Hi, Mick McQuaid here with the first of three videos for week two. So they're 02A, B, and C. And the first one is terms. So I'm going to pour a lot of terms on you, and um, I hope you'll be able to keep them straight. It's kind of tedious actually. This is the worst of the three videos, I'm afraid. So look forward to two more interesting ones later. So terms. So there are some basic terms, a database, and we've said already that it's a structured collection of data. A relational database stores data in self-describing tables with relationships between them. So we're going to explore the concepts of keys, which identify the relationships between them, and metadata tables, which are the self-describing part. A relation is a table in a relational database. Now, relation can also, I should have actually added to this, that a relation can be a single row in a database because a database can be one row long. A tuple can be a row in a database, and it can also refer to an entire table because, again, an entire table can be one row long. An attribute is a characteristic or a property of an entity, synonymous with field or column. We'll generally use the word column, but all of these words, attribute, characteristic, property, and this is spelled wrong, isn't it? Synonymous. Uh, and field are all synonyms for column. There should be a Y in there. Okay, so a row is a horizontal entity in a table. A column is a vertical entity in a table, and a table is a collection of rows and named columns. What is a relation? A relation is a table, can be one row, but what is a table? A collection of at least one row and at least one column, and it looks like a spreadsheet, but it is constrained by more rules than a spreadsheet. And this is key. The fact that it's constrained by rules makes it much more useful than a spreadsheet because it can be shared among people who never meet each other and who understand the data without it being explained. Spreadsheets often have to be explained to new users of them because they have no rules and they're kind of ad hoc. And the order of the rows must not matter. A database administrator or the system itself can choose to reorder the rows, and no program that accesses the database should be affected by that. And the intersection of a row and a column is called a cell. And no two columns in a table can have the same name. I've said that before, but it is quite common for a column's name to be repeated in different tables of the same database. So for example, ID, the column name ID is often used to describe different um, keys in different tables of the same database. Now here we see an example of a table or a relation, and this table contains information about some books. And it's very incomplete, by the way, because, for example, The Hobbit occurs in many editions. All these occur in many different editions, and this one actually is a reference both to a single book and to a series of books. I guess this one is. I guess all of these are. Author is simple. Year is simple, except that year is often saved as an integer, even though we never do arithmetic with year, except maybe to find the difference between 2 years. Pages is often saved as an integer, even though we don't do arithmetic with that. So you could just save these as smaller uh, pieces of text. And of course, books, all of these books have more than one publisher. They've been published in different editions, and they have different ISBNs. Um, and you could categorize them and subcategorize them in different ways, and they've been sold for wildly different prices. So this is a very, very simplified table called the books table. And we can use this as an example for things, but keep in mind that this is very simplified. A typical database may have dozens or even hundreds of tables. Relational database, we said, is a self-describing set of self-describing tables with relationships between them. And self-describing means that for each table in the database, there's a separate table or tables that describes that table's structure. And those tables, which are the metadata of the database, don't have separate tables describing them. They're just standalone descriptions. So here's an example of a database summarized visually. So this is called the NYC Flights 13 database. This database contains flights emanating from 3 airports in the New York City area in the year 2013. And it lists all the flights that took off from either Newark, LaGuardia, or JFK airports. This is a table in that database, and FAA is a column in that table, and there are other columns represented by the ellipsis. There, all of these have, except this one, have um, other columns in them. So there's an FAA column that has the 3-letter abbreviation, like for example, AUS is the Austin airport's abbreviation. And among the other columns, I'm familiar with this database, so I know that among the other columns are the full name of the airport. Uh, Believe it or not, each commercial aircraft has a tail number, a unique identifier printed on the tail of the airplane. I guess this is maybe that doesn't work for helicopters. I don't know. But anyway, the tail number identifies all commercial aircraft, and this database saves some information about that particular aircraft, who made it, when it was built, and so on. So there are an awful lot of these. This table represents all the flights emanating from New York, the year, the month, the day, the hour, the flight number, the origin, which is a synonym for FAA. So this arrow here indicates that this primary key is here a foreign key. This is identical. These two 3-letter codes are going to be the same in both tables. Destination is also a synonym for FAA and represents some other airport. So this airport is one of EWR, LGA, or JFK, the 3 airports in the New York area. This one can be any uh, destination in the United States, including Hawaii. The tail number of the airplane involved in the flight. The carrier is an abbreviation, I think it's a 2-letter abbreviation for an airline. For example, United Airlines abbreviation is UA, American is AA, Delta I think is DL. I can't remember for sure. And then we also have the names of those airlines. We also have a weather reading that takes place every hour. So there are 365 days times 24 hours. So there are that many rows in this table um, for weather reports at a particular airport, at one of the 3 airports. Um, so times 3, so it's 365 times 24 times 3 rows in this table, although some of them are empty, some of them they didn't take weather readings. Okay, and so all of these things are uh, synonyms. All of the arrows represent synonyms, and these synonyms are primary keys in the shaded areas and foreign keys in the non-shaded areas. So the primary key for this table is all of these together. It's called a concatenated key because it's the concatenation of all 5 of these column names. So the structure of the database is called its schema, that contains a list of its tables, its columns, and the relationships. The data type is a characteristic of the data. So if the data is a number, that would be a type of data. A text would be a type. Date would be a type. The cardinality is the number of rows in a table. The domain is the set of values that an attribute can take on. So for example, if we have a states attribute in a table of the United States, the state attribute can take on any of 50 values. And in this case, year can only take on one value. In the case of this flights 13, year can only take on the value 2013. Month can take on any of 12 values, so the domain is 12, and so on. The primary key is a unique identifier. It can be a single column if that column has all unique values, or a concatenated key of multiple columns if no single column has all unique values, which is the case in our previous, let's just look at it again. So year is always 2013, so that's obviously not unique. Month, there are plenty of flights every month and every hour, but there's no case where a particular flight number that flew at a particular time is duplicated. A particular date and time is duplicated. Okay, so that's the primary key. Now the candidate key is the column that can uniquely identify a row in a table that includes the primary key, but there may be other candidate keys. And then a foreign key is a column that references the primary key of another table. And this is how we get relations between tables, is the foreign key in one table is the primary key in another table. So we can match records in one table or rows in one table to rows in another table. Some other advanced terms: a query is a request for data or information from a database. SQL is obviously the standard language that we have already discussed. A transaction is a sequence of operations performed as a single logical unit of work. And this is the main purpose of most databases throughout history, is to record transactions. That's generally what we're recording, is a bunch of operations performed as a single logical unit of work. So for example, if you take money out of one account and put it into another account, that's a single logical unit of work. And you don't want the money you don't want it to be, if it fails, you don't want it to fail in the middle where you take money out of one account and then it doesn't exist anymore, so you can't put it in the other account. The entire operation has to be one logical unit, so that if you fail to put the money in the other account, it doesn't come out of the first account. OLTP is online transaction processing. So that's a database that's optimized for handling many small, fast transactions. And OLAP is online analytical processing, a database that is optimized for large, complex queries. And this is usually not a database. This is usually a data warehouse, actually. And indexing is valuable to us. An index is a data structure that improves the speed of data retrieval operations on a database table. And luckily, we don't need to know the internals of an index. We don't need to know what kind of a data structure it is. We simply know that if we declare an index on a column, then retrieval of that column is fast. And unfortunately, writing to that column becomes slow. So that's the reason why we don't index every single column. So indexing is something that we use to speed up things that are read more than they're written. Normalization is the process. Normalization is one of the really key things that we'll learn in this class, is how to normalize a database. That's a skill that you need to have to work with databases, to create databases. Denormalization adds redundant data to a database to improve query performance, and this is how a data warehouse is created. A join is when we join two or more tables together based on a related column between them. So, for example, in the flights thing, we might want to know the name of the destination airport and the name of the airline serving it. And so we for a particular flight, so we join all three tables, the airport table, the airline table, and the flights table between them. A view is a virtual table based on a result set of an SQL statement. So this is a table that doesn't exist in the database, but it's just the result. A stored procedure is if we store a bunch of statements in the SQL language, um, they can be executed as a single unit, and this is very common because databases do a lot of routine things. The source of truth is a durable, reliable enterprise database upon which other databases can be constructed. So we want to have one big enterprise database that is our ground truth, and then we make other temporary databases out of that for special purposes. Triggers we're not going to use, so actually I'm going to skip that one. A backup is a copy of data that can be used to restore the original data in case of loss or corruption. And the guarantee that each transaction is a logical unit means that we'll have backed up everything that's happened. You know, the database um, stops at the end of a transaction. If a transaction is in progress when the power fails or the disk crashes or something like that, only up to the beginning of that transaction is saved and can be backed up. And when we recover a database, we recover it to a consistent state after a failure or error. And these properties, atomicity, consistency, isolation, and durability, are necessary for reliability. These are the properties of a database that a database must have to be a reliable, durable database. A constraint is a rule that forces data integrity in a database. So we will learn how to make some constraints. And an anomaly and we'll discuss this if we haven't already. Insertion, update, or deletion anomalies are issues in a poorly designed database. Okay, so that's enough terms for one day. I hope to engage more of your attention for the next two on entities and data collection. Thank you for watching.